So first thing I'd like to do is set some expectations on what's going to happen here. I have to add this in, I hadn't thought about with cryptocurrency. We won't be talking about cryptocurrency. What I hope to give you is a working understanding of some of the terms, the common terms used, and the key drivers for choosing cryptography methodologies, algorithms, and strengths. So you won't leave here being an expert. Hopefully you'll leave here with enough information to make intelligent decisions about what you're doing with cryptography. So the first thing we should go over is what is cryptography. And if you're like me, the first thing that you do is you go look at Wikipedia. And Wikipedia has this moderately well-defined definition. It's the practice and study of techniques to secure communications in the presence of third parties called adversaries. And what I like to focus on is the fact that we're securing communications and that there are adversaries, right? You don't have to study it, right? Unless you're a cryptographer, you don't need to study cryptography, but it's important to understand that what you're trying to do is you're trying to secure communication, even if that's just communication with yourself, storing it on a hard drive, sticking it in memory across the network to yourself. It's still communicating, and there are adversaries that will try and get it. So how cryptography works. The first thing to understand that cryptography all starts with secrets. So secrets are an essential part of practical cryptography. You can have cryptography without secrets. It's just not a very good idea. But secrets have been in use longer than cryptography as well, right? There's very old stories about using passphrases to gain entrance to things. A very famous one is open sesame, to be able to gain access. And that was a secret, right? In the United States, during Prohibition times, there were places called speakeasies where you could actually go consume alcohol because you couldn't anywhere else. And you would have to have a proper passphrase to know that you weren't an official trying to arrest them. In ancient cryptography, they used methods. The cryptography methods were secret. And so you would have to know the method, but that was the secret part, right? How you would actually go from the plain text to the ciphertext, from the ciphertext back to the plain text, that was the secret. In modern cryptography, the methodologies are well known. They're documented, they are peer-reviewed, they go through this large process to be accepted, and they're published in academic journals. And oftentimes they're turned into, if they succeed and they're accepted, they turn into distributable libraries. In PHP, we have Encrypt, OpenSSL, and Sodium, and there are others. So secrets in modern cryptography is done in the form of keys. And those are what we use to add to an algorithm to turn plain text into ciphertext and back the other way. Generating and exchanging keys, though, can be a tricky business. Before the mid-70s, 1970s, passing secrets was a thing that people did with briefcases and handcuffs and long trips. As you would have someone with the secret, with the codes. In World War II, it was code books. You would have to just pass around you'd have to pass around secrets so that both of you knew what the secret was for today, or the secret was for this time, or the secret was for this message. So in modern cryptography, to make that usable and affordable and accessible, probably the most critical advance would be key exchange. So some of you are familiar with Diffie-Hellman key exchange. And what Diffie-Hellman key exchange is the ability for two people to have a secret value, to be able to come up with a known common value, but never pass the value across the wire. So when you make a connection to a web server that uses TLS, often referred to as SSL, this is what's going on in the background. All right, this is the Diffie-Hellman key exchange. And it's a process, I won't get all into it. You can read about it. That's actually a picture from Wikipedia. So there's really good information on Wikipedia on how that actually works. I've also got some references to some books that go through it really well too. But it's a way to actually come up with a common secret from your own secrets, never pass them around, and you can both communicate in a secure manner. And to do this is very expensive. It's using prime numbers, very large prime numbers, and modular arithmetic. So it's kind of this black box of magic that happens, which isn't so important for us to understand today. Just to understand that this is what happens. And you're exchanging a key. And key exchange is a really big, important thing. If you've ever had to converse with a third party, like if you use Amazon or if you use GitHub, you're communicating over TLS via SSH using an SSH key. You have to move that thing back and forth, that key, which can make it difficult. Key exchange makes it so that you don't have to do that. The next super awesome piece of voodoo mathematics that came about was public-private key pairs. And this is so you don't have to exchange secrets. So much like key exchange, the Diffie-Hellman key exchange says, I have a secret, you have a secret, we're going to create a combined secret. Public-private key cryptography says that I have a secret, and I'll give you just enough to do what you have to do on your side, and then you'll give me your public key, which has just enough information to do the same. The most famous one of this is called RSA, named after the three inventors of the process. Also, before they invented this, there's actually a British mathematician that came up with it, basically designed the same thing before they did, but it was super secret because it was part of British intelligence. So he was not allowed to tell anybody for a very long time. But asymmetric key cryptography, which is what the public-private key pair is talked about, made it so that you didn't have to do that key exchange. So it made it a lot easier to move data without having to do this complicated process of doing key exchange and building that in. The other part of cryptography is ciphers. So keys and ciphers. So we see some ancient ciphers here on the left. That's just basically a replacement. On the top right is, that is ROT 13, I believe. No, what is it? ROT 3, yes. Very, very simple. But that used to be considered acceptable cryptography 20 years ago. And in the bottom, that's RSA. So modern cryptography ciphers use mathematics, very complicated mathematics. And we'll get into that a bit more later. Just to understand that it's all math. It's why you need computers to do it. It's because it's all mathematics. There are different ways that cryptography is used, and we'll go over that as well. So the important things that we'll talk about that are happening in the daily life of a developer, someone who is writing applications, are going to be encryption, digital signatures, key derivation, and hashing. And key derivation is what a lot of people call password hashing. Even in PHP libraries, we call it password hashing. It is hashing, but it's a process of doing multiple hashes in different methodologies for generating keys. So they call it key derivation. So encryption. Encryption is used to place data in a form that can be reconstituted into its original form. So what can be encrypted can also be decrypted. It comes in two flavors: symmetric, which is a shared key, and asymmetric, which is public key encryption. So in asymmetric encryption, you have a shared secret. I'm sorry, yes. In asymmetric encryption, you do not have a shared secret. That's symmetric encryption. Asymmetric encryption, you have your own set of keys, and they're different. And what you're going to do is you're going to use a public key to encrypt data for a private key. And digital signatures go the other way around. I'll get more in depth in that in just a moment. Symmetric encryption is where you share a same secret, the same key. The same key is used to encrypt as to decrypt. Hashing is where you create a representation of the value, and it cannot be reversed. It's reproducible if it's a proper hash, but it cannot be reversed. So when you hash something, it doesn't normally have enough information to regenerate it. On this particular input, the input is smaller than the hash, but more often, if you see when you're downloading a file and you see that it has an MD5 or a SHA hash, that's a much smaller representation. And there's not enough information to recreate it. But the function allows you to come up with a string of the same length every single time. And the difference between a good input hash and a bad one is how well it prevents collision. What you don't want is you don't want two things having the same hash. It will happen because just the way that the algorithms work, you're just going to have that. So the larger your hash, the better the algorithm, the less likely you are to be able to create that. We'll get into that more also. And a modern hashing algorithm won't create an input, or won't create a collision for an input whose size is equal to or less than the value of the hash. So because it's the same size, you can't have a collision. It's only when it's larger. So if you have a 30-character string and you're doing a 48-character hash, you never have to be concerned about collisions because they just can't happen on a proper algorithm. So in our example, our input size is less than our output size. It means it would be impossible to create another hash. But if you have a larger value, like this image, it's condensing it down. And there's a popular attack that's been recent called Shattered. Has anyone heard of Shattered? All right, we do have crypto geeks. Okay, so Shattered is possible using a PDF to adjust the headers in the PDF until you can have a different document with the same hash. So you're taking something that is not necessarily the same size, and you're condensing it down to the point where you can keep adjusting the headers. You would change what the document is, and oftentimes that is I agree to do something or the terms of a document. So if you sign a document, if you sign a PDF, and you hash that, that should be secure, except if you're, depending on what you're hashing it with, and Shattered is for a SHA-1, which is an older hash, you can create the new document that you want to interpret as being signed, make it and do brute force. You make a hash, does it match? No. Change the headers, does it match now? No. Change the headers, does it match now? It's possible, albeit expensive. So in order to do that, I did the math on AWS, and before discounts, it would cost about $10,000 in GPU rental on AWS, and it would take a week. So it's a lot of these things when you hear about things that are possible to do, it's getting easier now that anyone can go rent 10,000 GPUs, but it's still prohibitive. And there are also ways around that. You can use a SHA-2 and use another hash as well, an MD5. So if you hash it twice using two different algorithms and you have two different values, it's nearly impossible to find one. Not impossible, but nearly impossible to find one that you could be able to create both with. And it would take a lot more time. Hashes, although fantastic, by themselves aren't terribly useful. Because all the hash tells you is that is the data that you got. So if I download a file and the hash matches, fantastic. That's the actual data that was there. But who's to know that the hash didn't change with the data? An attacker uploaded a new file that has malware in it and then generated a new hash. It's perfectly acceptable. I'll download it, I'll verify the hash, the data's good. So what you want at that point is digital signatures. Digital signatures are hash mixed with a key, with a function that uses a key. So it's not like you would just stick the key on, stick the hash on. And so that's going to verify the integrity of data, as well as the fact that the individual that you are assuming created the data did create the data. And so a digital signature looks very simple, like a hash. So these are HMACs, and it follows the same thing. And there are some rules that are required for an HMAC. And that is that if you have the same data with the same key, you get the same signature every single time. That's kind of a requirement. If you have the same data with a different key, you get a different signature. Because that's to prevent someone from being able to say, here's the data you got from person A, but person B signed it. And if you have different data, it will be different as well. So it's very similar to hashing, although it's putting that key in there, that secret value that no one else should be able to know, that can tell you that I'm signing it and it's me as an individual signing it. So if you sign your GitHub commits, which I have to, you're doing this. You're saying that I, as an individual, signed this, and you can trust that this commit was made by me, not because it just has my email and my name on there, because anybody can put that in, but because I have provided GitHub with my public key, and it can verify the signature that I made with my private key against the data. Key derivation is another really good use of hashing functions. So key derivations are cyclical hashes where the hash is fed into the algorithm over and over again to generate a brand new hash. It's done many times to require a lot of computing power. The idea behind it is to require a lot of computing power. Hashes should be very fast. If I need to verify data, I should be able to do that very quickly. The faster, the better. However, for passwords, I don't want you to be able to try them constantly over and over and over again. I want it to be very difficult for you to be able to brute force a password. So key derivation, by design, is very computationally expensive. And it also uses, in good methodologies for key derivation, they use random values called salts. And the salts are used as well over and over again to create this different value. And I'll show you a very oversimplified value or oversimplified example of why that's necessary. So I hate passwords is actually one of the top passwords in use today. Mixed with a random salt, get you a random value, the hashed value. You take the hashed value and the salt, you get another value. And you do it again and again and again. And so that's how you're generating, you're basically going over and over again to make it computationally expensive, which is important because the way that passwords work is you're trying to give your users time to change them. One of the nice things about passwords, as opposed to biometrics, is you can change them. It's important to secure these things in such a manner to buy your users time. So if your site gets attacked, and you may just have a simple blog site, and many people think, well, I just have a simple blog site, what do I care? Unfortunately, your users probably use their email as the username, and they probably use the same password for their email that they did on your blog. Most people don't know better, and that's what they do. And if I can hack your site and get their password, and I have their email, and then I can get their email account, I can now do password resets on every other thing that I want to have access to those because those are always sent to email. So I can get their bank account, I can get their credit cards, I can get enough information from there, I can get onto their shared drives where they probably have their tax statements that have personally identifiable information, enough to impersonate them however I like. So if you only have a very simple site that you require people to log into, try and be very careful with what you do with their passwords because, again, if users are impersonating people on your site, you may not care, but your users don't know security and they're doing terrible things. Like some of you may also have just gotten very scared when I told that, as I did when I was first told these types of things. I didn't know any better. I figured, well, I'll have certain types of passwords and that'll keep me safe. But again, it's important to, as you're using these key derivation functions, you want to make them as strong as you possibly can, as many iterations as you can stand. Because what that means is if you're using the password functions in PHP and you go through a large number of iterations, every time I want to try and attack your passwords, I have to do a large number of iterations every single time for each attempt at a brute force. So how many people here remember Ashley Madison? The talk about Ashley Madison, right? All right, that's a little more popular. So Ashley Madison was a website for non-marital affairs. Most of the individuals, most of the men on this site were marital. They were also, because of the way the site worked, they tended to be unusually important. A large number of military, government, and high-level C-class executives information was found on this site. And it was PHP, and it used the password function, which meant it was very secure. So the people attacking it, after they were able to, there's this thing called the top 100 passwords. It's a list that people keep updated from things they've been able to attack. And they said, I'll try the first 100, which gives you anywhere from 10 to 30% of the password base. And then they just stopped because it's just too expensive to try and just brute force all the other passwords, one character at a time. Until they found a backdoor because they had left in a separate hash, non-key derivation, that was built using the username and the unencrypted password and the unhashed password, which was just a SHA-1. And so using that, using the known username and the known symbol in there, they were able to just generate everybody's passwords. So always important, key derivation, because attackers will just walk away more often than not, because they know that by the time they are able to crack it, the users will have changed, most users will have changed their passwords. And that's why key derivation is important. So getting good cryptography. We have a kind of a basic understanding of how cryptography works. The key to your own implementations will be using good cryptography. And cryptography has been used for centuries with varying levels of success. Many of us have likely used bad cryptography at some point. And if you're as old as I am, it may have often been good cryptography when you started using it, right? That's like using an MD5 or a SHA for a password. 12 years ago, using a salted SHA-1 for a password was considered the best password security available, and it was just fine. But today, I can crack that on my phone. So as technology increases, so does the need to use better cryptography. But it's important, I think, for you to understand what makes good cryptography, because what is good cryptography changes. Throughout the years, it will change and change and change and change. PHP 7.2 is taking us to a new level of cryptography with libsodium. But it's important to understand why it's important and what makes it good. So good cryptography obscures data in such a way that it's difficult and costly to duplicate or reverse. Right? Just as we talked about with the key derivation, it's making it very expensive to try and get someone's password. When you're using algorithms, you want them to be very costly and difficult because it's going to make it harder. And there's a very good reason for that. And we'll talk about kind of how this works and why it's important into two different sections. Entropy and computational cost. And if you don't know what entropy means, we'll get into that as well. They're independent as well as interdependent. So things that can have good entropy have nothing to do with the computation, but together they create good cryptography. So when attacking it, there's two ways that you can attack cryptography. One is pattern analysis. The other one is brute force. And pattern analysis is, you often hear it referred to as cryptanalysis. That's taking some information you know about the subject, a raw subject, and seeing if you can determine patterns. And the other one is just trying it again. Is this it? No. Is this it? No. Is this it? No. That's brute force. So brute force is much like smacking a rock with a hammer. If you hit a rock with a hammer long enough, the rock will break. Depending on the size of the hammer is how long it will take, right? Because you could sit there with a very small hammer and just keep hitting the rock. If you've seen very small streams cut through rock over centuries, right? It's possible. It's just difficult and costly. In cryptography, it's just trying it over and over again, all right? Is this it? Is this it? Is this it? Trying the combination. But based on Moore's law, the hammers get more powerful. Every year, more processing power, more processing power. And with network computing, you can get multiple devices working on the problem at the same time. And with cloud platforms, you don't even have to purchase it, right? You can just rent the processing power from the cloud, or you can build new hammers. So these are ASICs. This is application-specific integrated circuits. And all these things do, if you know anything about cryptocurrency, these are miners. And all that they are programmed to do is generate hashes. They are extremely fast at generating hashes. There's also chips that are very good at math. So this is an NVIDIA GeForce chip, and this is a GPU. GPUs are very good at making mathematic computations. So if you're going to try and break some encryption, this is fantastic. They also do really well at generating hashes. And we won't even get into the quantum problem. Right? There are some algorithms that are available in PHP that are considered quantum secure. And it's not because they can beat quantum computers. It's just that the algorithms were made with a type of complexity that makes it difficult for the current quantum computers to do. But nobody's going to be using quantum computers to break your encryption today. It will be the quantum computers of tomorrow. So we'll see where that goes. But there are ways to fight all that power. And algorithm complexity is one of the top things there. Harder math requires more computation. So the difference between algorithms before and algorithms today is that the new algorithms are more computationally complex. It requires more CPU to generate the encrypted value or decrypt the encrypted value back to plain text. And history is littered with algorithms that were too easy to brute force. Encrypt is no longer in PHP. That explains everything. Right? It had algorithms that were so old and so outdated, and the fact that the library itself was taken away because it was too old. But most of the algorithms that were available weren't even considered safe. Right? So when I started using PHP a lot, 10 years ago, triple DES was considered safe. It's now considered completely terrible. Don't use it. AES is the new standard. But now that's changing as well with libsodium. So it's constantly evolving to create more complex algorithms. Large keys are also very helpful, depending on your algorithm. Specifically, very large prime numbers in asymmetric encryption algorithms. So anyone here have to update their website to something larger than a 1K key a year and a half ago for Google? Nobody? Host a website and Google said, you need to change this or we're going to lower your rankings? Okay. So Google, I believe it was about a year and a half ago, said if you don't have I think it was 3 years ago, they said if your site isn't secured by SSL, you're going to drop in the rankings. And everybody said, oh no, SSL. And Let's Encrypt was born, right? The easy and free way to do SSL. Shortly after that, they said 1K keys are not enough because there are a lot of sites with 1K keys out there. So 2K keys are required. And that's what we mean by large keys. What a 2K key is that's a 2048 byte integer. It's a very large integer. And it's not just an integer, it's a prime number. So just finding a prime number that size is very difficult. Doing math on it's even more complicated, which makes it difficult to brute force. If you're using symmetric encryption, your larger key means as they try and brute force, it's more combinations that you have to try, which makes it, again, more difficult. So the larger the key size, the more secure. System resources. Requiring large amounts of system resources can prevent the ability to use the things that you're not expecting to use. Something like an ASIC or GPU. They're very good at doing little things, very small computations, but if you require that they use 2 threads, they can't do that. Or if you require that they use 100 megs of RAM, they can't do that either. Or even a meg of RAM on most of them. So you can increase the complexity by adding in the requirement for using memory or using a number of threads, which is what the new password stuff does for libsodium and the Argon 2i implementation. Iteration. So in iteration, you're just doing it more times, right? So whether it's more substitution inside of your encryption algorithm, that's part of making them more difficult, is that they do more substitution rounds, they do more mathematic rounds, your binary mathematics, makes it more complicated and makes it more expensive to do. And then password hashing is the big one, right? Where you just do it again and again and again and again and again and again, as many times as you can bear. And that will do that. So the other tool for cracking is cryptanalysis. And cryptanalysis, I show the puzzle up here because in World War II, these are the people they would find to break codes. They would find people who are really good at crossword puzzles. Because crossword puzzles, you'd have a question, you might have 2 or 3 of the letters, and you'd have to come up with a word that would match. So you'd have to have the subject matter and a couple hints, and they could find the words, which is basically what cryptanalysis is. Today, we use machine learning, right? We don't need people, we have machines. So mixing the knowledge and identifying the patterns to fill in the blanks has been used for years, but today, brute force is usually easier, but if you could reduce the cost of brute force, you're going against what you're trying to create, right? You're trying to make it more expensive and more difficult. If you can reduce the amount of effort you have to spend in brute force by understanding what certain pieces are most likely to be, then you're reducing that cost for brute force. So entropy, we talked about this a little bit earlier. Cryptanalysis is fought with entropy, removing order and creating the appearance of randomness, right? In computers, there is actually no such thing as random, but we can try and make the appearance of randomness. As individuals, we cannot do random because we have our own biases, our own bias, and we were more likely to come up with the same, if you said come up with a random string in your head, if you wrote them all down, you would come up without, eventually, if it was a large enough list, you would see that a certain number of values would come out more often than others because it wouldn't be random because your head doesn't work that way. And computers are programmed to do the same thing the same way every single time. If a computer does something random, you have a problem. We call those bugs, right? So trying to get computers to do random can be difficult. And real-world data has very predictable patterns, which is why entropy is such a big deal in computing. So if you take, for example, an HTTP message. So this is a very standard HTTP message where you make a request to get information, and it's going to give you back data. This is the response, right? So I'm asking for account information, and it's returning me account information. So JSON responses look very similar. I can very easily guess, just by looking at someone's API documentation, what these pieces will be. I know that I'm going to be getting a 200 response. I know the content type is going to be application JSON. A very quick query will tell me what the server name and version is, and I know what the fields are going to be. All of that is going to always be the same on every response unless they change the server version or they change their API. So I can very quickly predict most of the data in this response. Other pieces are highly predictable. If I know when I'm making the request, I will know what the response date is going to be, right? For 1 second, I will know. And then the next second, I will always know, I'll also know. So I have a second to try and do terrible things before this is not valid. But honestly, how many people validate the response times? Right, so it doesn't necessarily matter. It just has to be a time, if you're even looking at that header at all. Other data also has predictability. So dates of birth. There are people that were born more likely on particular years than other years. There are people that are, if you'll notice, birthdays tend to fall on particular months as opposed to other months. Less predictable now, based on the fact that everybody lives in, well, many people live in climate-controlled environments. People that would be in this type of database probably are. Names. There are a limited number of names, and you can definitely determine that a certain number of names are much more popular based on the language and locale than other names. So there's predictability there. And then some sort of identifier. Most countries are going to their country identifier becoming random values. Some of them used to just be counters. So based on the date, I had know the range, the date of your birth, I know the range of your ID number, your country ID number. Again, that's changing. Credential data is also highly predictable. Most services use email for the username. So if I know your email address, which most people don't think is being terribly private, it passes around on cards, it's on it's on your Twitter account, it's everywhere, right? If you use that as a username, then I have half of what I need already to attack you. I have half the credential. Passwords also have a high predictability use. So 68% of people reuse their passwords. So that means that I will use a single password on more than one site. I think that's low, but in 2015, that was the value, right? And the top 25 passwords, so when you get all the passwords on these nefarious dark websites, these paste bin sites that you yourself can go find everybody's passwords on paste bins today. The top 25 of those constituted over 50% of the passwords. So if I get a password database and I just try and the top 25 passwords, so each one of these items I try 25 times, I am 50% likely to get it. I'll be able to hit the password in 25 tries. That's problematic. Nearly 17% of users safeguard their accounts with 1, 2, 3, 4, 5, 6. Very scary, but most people hate passwords. I hate passwords. I have pledged my life to getting rid of passwords for the last 3 years, but they're there. And people hate them, and they just want something they can remember. So they will do the minimum necessary to get past the password policy. Most users will choose passwords based on the ease of recall, right, rather than entropy. So because of that, the reuse and the predictability creates a serious problem. As people who are trying to secure the web and protect people from themselves, we have to create the lack of uniformity across our data set. So if you take a look at this data set, if you're like me and notice patterns very quickly, you will see things that are matching. These are 3 users with the same password, right? So as that said, 15% of your users will have the same password, 1, 2, 3, 4, 5, 6, right? So what you're trying to do is you don't want them to be able to single it out, because without having to run a single query against, or a single attack attempt, if I can see in the data that 3 out of 5 of these are the same, I'm going to guess that's 1, 2, 3, 4, 5, 6 just by knowing passwords. Or that's the same user with multiple usernames. But you will have commonalities across the data set, right? In your password database, 25% of the people will be 1, 2, 3, 4, 5, 6. So all I have to do is go through there and find it. So good cryptography uses random salts to add entropy to hashes. So you add the salt to the password, and now they're all different. And that's why you put salts onto passwords. It's so that you cannot use the known tendencies for passwords against your database, if you're ever wondering. But nearly every type of data has recognizable patterns. So English as a language has patterns. Spaces can be determined very predictably. Most languages, spaces can be detected very predictably. Single letter words have a very limited number of characters. 2-letter words are very predictable as well. 3-letter words, and then the most common letter in all the words. If you don't add some randomness to that, it'll be very easy to predict what they are. So this is actually using really good encryption without using entropy. So you can see that this is encrypted birth dates, or just dates, right? So the first 2 are the same. We don't want that. But even if they weren't the same, they're all very similar. Most of the data in here is the same. So this is encryption using an auth tag, which is a hash. This is very modern encryption. So modern encryption doesn't help you without adding entropy. The only difference in these things is one letter, or two letters, two different segments. But in the first segment, there's only two options. In the second segment, there are also only two options. So this is very, very recognizable patterns. So using randomness in a random initialization vector in encrypted data, they're all different. So that's why it's important to have randomness in encryption as well, because you want to make sure that that same data isn't the same. So random salts and IVs are necessary. Necessary. Unfortunately, it's easy to get. So C-spring, cryptographically secure pseudo-random number generation. Big word, just use random bytes, right? PHP, random bytes. That's all you need. It does all that for you. The big word you don't need to remember. If you need to generate an IV, if you need to generate a salt, random bytes. It's going to do all this stuff to make sure that it actually is random, it's not predictable. Because if you don't, people can, based on the time that you execute it, have a fairly high likelihood of figuring out what that value is when you generate it. So you want to make sure you're doing it properly. All right, I've just thrown a lot of data at you. And it's been like 40 minutes. So what I can tell you is that today, you can do very, very simple things. Use the password extension. PHP has the best password option on the planet. I have worked in a lot of languages and there is nothing better. It's very simple to use. You can very quickly determine if it needs to be rehashed based on a new algorithm. You can upgrade the algorithms in place. It has very sane defaults. Just use it. Because when you need a new hashing algorithm, you can very quickly just change a value from password default to pass1 argon 2i, and you now have argon 2i. And you can rehash in place. So just use it, just use it, just use it. If you're using a framework, make sure they're just using it because it makes your life easier down the road, I promise you. Libsodium, brand new in 7.2. Documentation is terrible. I'm trying to work on that. There is no documentation, right? The person who wrote it has a patch for it. I'm trying to work to help him get that patch into the PHP docs, but we'll see how that goes. But we are working on it. And it actually simplifies encryption. If you've done encryption before, when you need a key, what size key do you need? I don't know. Let me look at the docs, right? It's very complicated, very difficult. It just gives you a constant to do that. It's very easy to generate the nonce, go through all these things, and very quickly do it, right? You don't have to guess anything. You don't have to know anything, right? You just call the function, pass it their text, the key, and the nonce, and it encrypts it. You don't have to guess algorithm. You don't need to know strength. You don't need to know iterations. It's just going to do it. It's supposed to be simple. The only thing that's not simple is the length and the names of the functions and the constants, because they are really, really, really long. I do a talk just on that, and sometimes just the function takes up the entire length of the screen. It's complicated, but it's easy. Okay, libsodium is easy. The password function is easy. And at least now you know why you should use them, because it's important. Introductory books. So the code book is a really good storytelling book about how cryptography worked over time. And it gave me a lot of insight into why is this way, why is this that way. If you're interested, it's a really good book. If you want to get deep into crypto, Cryptography Engineering talks about if you're a math geek, talks about math algorithms and explains the math behind it. So if you're someone like me who better understands physics when you can do the math, this is a good book for you. If you're not one of those people, you can just skip the math and it'll still explain it pretty well. And then Serious Cryptography is a new book that I'm reading that's actually pretty good. It does really good with randomness. There are websites. So the password manual, it actually talks about it fairly well. If you want to use Sodium, the PECL documentation is identical to the PHP extension. And you can also start using libsodium today using the PECL installation. There's also OpenSSL and C-spring. The information is there as well. And then a lot of the things I learned about cryptography, I learned from Wikipedia because it really has really good information on how does RSA work, how does elliptical curve work, what's an ED 2509 curve, those types of things. So check that out if you want to get really, really into it. And then we have like 30 seconds for questions. Questions? Okay, if you have other questions, which you probably do, but you're forced for time, I'm going to be here all week. So please just come see me and flag me down. I love talking about this stuff. Check out the books. I'll put the slides up somewhere so you can go through those again. And thank you for coming.